Okay. Good afternoon for the people here, and also we know some people online. So good afternoon to all of you. And today, welcome to this public talk. And later, we're going to have a ceremony for this year's our best research paper award for our junior research investigators. Today, this year's, last year actually, 2022. The winner is Mr. Atiq Rahman. Congratulations. And this is actually part of the whole ceremony. Before we bestow the prize and the plaque, and we're gonna ask Mr. Atiq Rahman to give a public talk on his work. Okay, so now he's currently under the supervision of Dr. Lin Zixun, right? So I will let Dr. Lin introduce our speaker.
Okay. Good afternoon, everyone. So let me give a short introduction to our speaker, Atiq, today. So Atiq got his master's degree in Pakistan with the study of Korean noise in the silicon sensor in the CMS. So CMS is one of experiments at CERN, one of LHC experiment at CERN. So he then come to Taiwan for the PhD study in the National Central University. So, and I believe that at that moment, he saw that he will continue his study, his research in the LHC experiment at CERN. But when he come to hear that he found that our project in the gamma ray medical image is more interesting. So we are happy he decided to join our group. So for this study, so he mainly worked with our project scientist Mitra and Professor Zhou from NTU for this image reconstruction software and this deep learning application in the medical physics in the image physics. So so thanks to the institute that to give for this honor to the Atiq, and this also encouraged us quite a lot for our whole group. So let's welcome the Atiq to present his work in the deep learning application in the image constructions. Okay, thank you.
Pointer. Professor Chang is my supervisor, and Dr. Mitra is my advisor in academia Sinica, and PI is CH Lin. These are the outlines of my today's presentation, and I will briefly talk about the background and motivation of this study, and also work methodology, and talk about the results, application, future prospects, and we come on the conclusions. Before I go further in my talk, I want everyone to take a look and keep the flash of this slide in your memory till I finish the talk, that how many people have been died due to the cancer in 2019. And this data is published by the one collaborator of the World Health Organization. due to the cancer, due to the dementia, Parkinson's disease, and as a physicist, how much we can invest our energies into the health sciences and the leading health issues. And also, many people who got the cancer, they adopted different treatment methods, and we can what we can do in terms of detector designs in imaging physics and radio in for the dose measurements and other many applications, and there are a lot of scope what we can do. I will talk about the classical problem called inverse problem, which is the bread and butter of the experimental sciences, where we have a measurement on the detector and we have a source signal, and we want to get the source signal from the measurements. And inverse problems can be categorized into the two kinds: well-posed inverse problem if they have a unique solution, and if they don't have a unique solution, a zero solution, they are ill-posed inverse problems. And of course, inverse problems have a lot of scope, but I will talk about only in the imaging physics, and especially in positron emission tomography image reconstruction, where we inject some radioactive source to the patient, and that radioactive source emit a beta positive, which annihilate with electron from the environment and from the tissues of the patient, and annihilate into back-to-back gamma to conserve momentum. We put a detector around the patient, and we reconstruct the source distribution. So there are two major scopes of the PET detectors in imaging and also in radiotherapy. In imaging, we use PET to diagnose the metastasis tumor and the metabolic activity in the patients, and we also can use this as a QA tool in the particle therapy. Let me tell you, the particle therapy is a way to kill the cancer, and the classical technique to kill the cancer is X-ray therapy, but particle therapy is better than X-ray therapy because of the localized energy loss and Bragg peak location, and people are more using particle therapy compared to the photon therapy. Now I'm going to categorize the way we get the image in the diagnosis from the PET for the in the case of diagnostic imaging. We have a cyclotron on the side of the PET detectors. We get the isotopes from the cyclotron and mix them with some glucose or some tracer and inject to the patient, and patient is under the detector, and we reconstruct back-to-back coincidences, and then we reconstruct the thanks to the abnormal metabolic activity in the tissues, we can construct the source distributions, and this is some spread of metastasis in the human body, and you can see how metastasis can be detected by piling of the source distribution. Here is why we use PET as a QA tool in the proton therapy. For this, I have to go to tell you here, you see that proton beam have a localized energy loss, and if there is some source of uncertainty, if there is some source of uncertainty coming from beam energy from patient misalignment or the CT units conversion, we can shift. It is possible that the Bragg peak positions may shift, or the dose may increase or decrease, and this can be very challenging because this is a case of some lungs cancer, where tumor is adjacent to the heart. Heart is the organ at risk. And if you want to kill the tumor in lungs, then it's possible that if any source is active, of uncertainty source is active here, it may lead some imprecise results and do more harm than the betterment. So doctors and medical physicists give us some regulations and the grass volume for the tumor, and also the volume, clinical volumes for the dose, which are the safe and which are not the safe volumes. So we have to follow them, and that's why we use PET to track the dose. And we can use in proton therapy to track the dose, thanks to the relation of proton therapy, proton dose, and the relation between the PET activity. You can see there is a proton beam going inside the tissue, and this is a proton dose, and there is a relation between the PET activity and the dose. So once we have the PET activity, we can translate into the dose. How we use PET activity, we have a patient, let's say we take it into the treatment room and we irradiate a proton beam, and it will create some isotopes along the patient, and these we don't have to inject any isotope tracer now, because this proton beam create inelastic interaction and create isotopes, and we put a detector around the patient and reconstruct the PET activities. And the same we do with the virtual beam on the patient CT, and we generate the PET activity. Any mismatch in the PET activity will be will help us to know the dose mismatch and discrepancy in the treatment plan. Now, in this slide, I will talk about the imaging physics involved in the PET image reconstruction. Here we first model the radioactive tracer, and then we have an imaging model for our detector, where this is a linear model, and Q is here the projections, A is the system response matrix, and then we also model the data or the measurements, and we then the third part comes where we want to estimate the final image from the data, where we estimate the final image from by indirect approach. We have the projections, and we estimate the projection using the response function, and by reducing the distance between the projections measured at the detector and estimated projection, we improve our source distribution, and we have a loss function for that. And we also can introduce regularization, and the weight of the regularization is here beta, which depends on the fidelity of the data as well. This is the pictorial view of the method we adopt in conventional reconstruction in the diagnostic PET or any other purposes. Here we initially get some source distribution, we forward project using our system response matrix, and we estimate the projection, and we also have the real projection. We get the difference, we back project them, and then improve over measurement, improve over image. But beside this method, we also can use we can reconstruct the image using maximum likelihood method or any other method. We still have some backdraws that we can we have noisy data. We don't have that model, exact model for the noisy measurements. We have to add some regularization, which are handcrafted regularization. The response function for this detector is really time-taking and really big deal. And we also don't include any patient information, and this response function is usually a geometric response. So, and this is static, and sometimes we need really a lot of data to reconstruct the image. So that's sometimes exceed the normal dose limits for the patient. So what we have, for this we have a data-driven solution to solve the inverse problem, where we have the source and measurements maps. And here we don't want to reconstruct the X, but here we want to get a transformation matrix as an inverse matrix to transfer our measurement or the projection directly into the signal space. So we assume we have the all data here. So the goal of my study is first to give an accurate technique to crack the inverse problems in the PET image reconstruction, and then as for the diagnostic PET. And also now I want to go one step further. I want to also predict directly dose for the from the PET just by feeding the detector data to my method or my model. So for this I use so what we can achieve from this new technique, data-driven technique, we can directly map the dose as well. And the time for this will, after training the model, will be very short to reconstruct the image. Is almost 40 milliseconds. And but comparatively here, if we want to get the dose, we have to have positron activity mapping, and then we will reconstruction, and then we will map this to again using another inverse problem to the dose space. And the time required here is depending on the detector size and also the FOV of the patient. So the other thing is here we do not add any handcrafted regularization. We can update our transformation matrix for the patient specific information, but here we are not able to do that. If we want to improve the image, we have to introduce handcrafted regularization in the classical imaging methods. So this is the methodology I adopted for my in my paper. That's because in data-driven we need data, but our detector we are using is a new detector, and we do not have a lot of data. And for this, I have a solution that I do all simulations, and I feed the simulated data to my AI model. I take a real patient CT and use a proton beam simulations to get the functional distribution of positron emitters, and then I read this functional distribution in the detector environment with the limitation, all physical limitation of the detector, and get the readout chain, and we get the coincidence data. From these two set of information, we get dose, also the functional distribution of positron emitters, and at the end of the day, we also get the coincidence data from detector model. So if we want to reconstruct the positron activity, we will feed it measurements and positron activity here. And if we want to reconstruct those, we will feed our model here measurements and those here. So next is the material. What I do, the CT image is abdominal CTs, and of these size I use the verified physics lists, and these physics lists are used by the medical physicists and also I use the different monoenergetic cases, spread out Bragg peak cases. Also I have some detector variables as well, the detector size, time resolution I use, energy resolution I use here. Next is the deep learning model. I use a deep learning model called generative adversarial network or model, where we have two models simultaneously being trained. And one is called generator, one is discriminator. Discriminator's job is to identify or classify the fake images, and generator job is to generate more realistic images. So this is kind of imposter, and this is a kind of detective. So they train themselves side by side, and once the loss function becomes to a saturation level, we stop the training and we can use the improved generator model as our final model. We will feed the condition data. Here condition data means our measurement data from the detector, and we have here also the target data. So we train our generator both for target data and also for the generated data. So we can train our model. Once the model is trained, we do not need any further training. We can simply use them. And this is the mathematics involved in this. Here is the simple inverse problem. And we have the loss function in terms of minimization, maximization of the loss function, where we minimize the distance between minimize the loss of the generator and maximize the loss of the discriminator. And we also introduce L1 regularization, which I will come on that as well. And this is entropy loss for the discriminator, both for the images provided from the target and also from the generator. So we also introduce L1 regularization in order, because we have the final target as well. So we use them to make sure that we are not getting some non-realistic images. So this is the pictorial view of my model. Here is upper is the generator, lower is the discriminator. Generator have two parts, encoder and decoder. The encoder part is do the downsampling of the features up to the bottleneck. Bottleneck is a dense feature map which is used for upsampling up to the dose as a reconstructed image. And we have CNN layers and no fully connected layer in my generator. And we use max pooling, batch normalization, dropout, and we do not use any fully connected layer in our generator, but we do use fully connected layers in our discriminator. So decoder also have the convolutional layers and all other layers, but we have the it do the upsampling. And this discriminator is a patch-based discriminator. And we have to define a receptive field. Here, receptive field is something we do the analysis or the estimation of the reality. I mean, the realistic image is a fake image. We decide by the receptive size or the receptive field. So this is some information about the hyperparameter setting and all the variables I used. So if you are interested, you can take a look. And I will come to the results. And here is the predicted result for the proton dose. And here, for training of such models, I use detector data and proton dose data for training my model. So here is the 1D profiles. And I also can do the reconstruction for the diagnostic PET as well. I mean, I can reconstruct the positron activity as well. And this is the result for the positron activity. And we also have a matrix, evaluation matrix. We use mean relative error. We use absolute dose difference and range shift in the Bragg peak as a metric. And here you can see the baseline for the absolute dose and range shift are for the uncertainty. For range shift is almost within 1% uncertainty, and for the dose difference is 2.5% uncertainty. We also have estimated how minimum coincidence data we require for the image reconstruction using deep learning model, because we cannot feed a lot of information to our model for reconstructing a single image. So we have estimated that 105K coincidence we require to reach 2 to 3% uncertainty in the dose. So this number is almost 8 times lesser than the conventional reconstruction method. So we do not need to inject a lot of radioactive tracer to the patient in this case. So we also have studied the stability of our model by introducing systematic variation in the patient by up to plus minus 10%, and we have seen that up to plus minus 8.5% our model is stable, and we can predict with this percentage of the variations. So next, I will talk about the applications of and the prospects. So we in the image reconstruction direct method for the we can use it to learn the imaging physics from the scratch, but we also can use a model-based physics informed deep learning model to do the reconstruction. We also can use this all reconstruction scheme as a final component to of the conventional reconstruction to denoise the image. We can also use the in the radiotherapy for different application, MR conversion to CT. We can use the incomplete CTs to convert them to the complete CTs, and we also can use this method in the perm gamma studies, and also some applications in the flash therapy. And future goal we want to do is we want to adopt this study to develop an intelligent image reconstruction tool for the multimodal for the different non-conventional detector geometries, where we have organ-specific PET system. Usually PET are very big and cylindrical PET systems, but we want to design some organ-specific PET, and that may be more cheaper than the full PET solutions. So present study is the first study in this direction, and we want to make our model rich and increase the capacity in the future. This is the last point, is very important for us to, because PET can diagnose the tumor, but beside that, PET also can detect Alzheimer and Parkinson diseases. So that's why I had marked the Parkinson diseases and Alzheimer disease in my first slide. You see there are some healthy and the normal subjects, and also Parkinson disease patients. So this is a normal subject and this is disease subject. Here is a normal subject and disease subject. So Parkinson disease can be diagnosed by the head images only. So, but usually PET images are very, scans are very expensive, even not available for all cancer patients. So definitely they are very inaccessible for these patients too. But they only need head scan. We don't need a full body PET. So why not we design small PET which are just focus on the brain or some organ, but we need a versatile image reconstruction techniques for that. We cannot somehow simply reconstruct for such kind of modular approach, images for such modular approaches. So we have to come up new ideas, maybe use AI, and also other techniques we can use as a physicist to make these PET scanners cheaper and accessible, because they are really very important imaging technique to decide at the spot, not only cancer but other diseases. And there are other as well, I didn't mention, but it is here. Some other diseases as well can be diagnosed. So we should invest on the such studies. So this is one prototype, a simulated sketch of our detector we have developed. And in future, we want to, we can still use this detector and use the image reconstruction at multiple angles, but we also want to increase the size and also want to make it for some organ-specific detector. This is the information about the geometry and the crystal and the readout. And here's the conclusion about this study, that we got the dose uncertainty up to the 2% and range uncertainty up to 1%, and we use 105K coincidences, and we have only used 5 minutes acquisition time for such a small PET. Our PET is actually really small. It's not really big PET module. So we all got with this small PET scan detector. So small flat panel detectors we have checked that can be introduced as a QA tool in the proton therapy. This is acknowledgement. I use some resources from AS Grid as well. And this is our team. This is Professor Lee. Everyone have familiar from him. And he's Dr. Mitra. He's sitting here. And CH also sitting here. And this is a Professor Chow. She is from NTU. And this guy in front of you. And this is a paper. Our paper has been published in this journal, Physics, Medicine, and Biology, and also recognized by the Physics World as a magazine news. So thanks for listening. Any questions?
Okay. So this is a public talk, so maybe we take 1 or 2 short questions before we conduct the ceremony.
Thank you, Atiq. One question I have is, perhaps you can tell a little bit more about this multimodal imaging, how you can expand this to include more modalities, and what are the advantages of doing this actually?
Oh. First, I will go back to the slide. Let me go. I talk about multimodal generative model for this modular PET detector. Usually PET detectors are very big and cylindrical, and they are really expensive. So not every patient can afford them. So we want to design small detectors which can intelligently modify their geometry. And I mean, it's not a magic, it's just to rearrange the modules and do the reconstruction for non-conventional geometries. So they can be for only brain and able to diagnose some diseases like Parkinson, dementia, or we also have in market already some kind of small solutions for small animal PET, but for human is more important. We can like some mammographs, some other applications. So we want to use our deep learning model to do that job actually. To help us for the image reconstruction as well. But of course, we can apply the conventional reconstructions as well. So this is really fascinating that these detectors can be used for instant decision by the doctor. So that's our goal that we can achieve. So what we can achieve. So, but do you have any comments for this?
Because you use only one condition, right? The detector information.
Yeah.
My question was more how you can enhance these modes.
You are talking about the imagery construction capability. Yeah. Yeah, because we only use one kind of information, that's coincidence information. We do not give the time information to our model. We do not provide the patient information of all patients. We do provide the CT information, but we do not provide a specific to the model. So we can introduce different kind of informations. We can feed different kind of informations to our model. That's called multimodal generative model. to help us to do the reconstruction. And we also can provide the energy information into our model from the detector, and also response information coming from the geometric response function. So we can expand this model in that way.
Thanks.
Thanks.
Okay, one more, Zumini.
Radioactive tracer for okay. Actually, I have not much idea about the drug delivery and the kind of the tracers used for brain scans, but I'm sure they are using. It's actually not radioactive tracer. They are checking the activity of the different hormones, like dopamine I think everyone is familiar, might be familiar from dopamine concentration. There's a kind of happiness hormone in our brain, and they not specifically looking at the some tracers, but of course they use some tracer, but they see the concentration because these hormones have binding or with some kind of drugs, so they try to guess the concentration of hormones using some medicines or some tracers. But I'm not very sure what kind of specifically they are using, fluorine or carbon or oxygen. I'm not very sure. But usual for PET scan, the people using F18 as a radioactive tracer. Yeah, I'm not very familiar from drug delivery, but yeah.
Okay, I think with that, let's thank Mr. Atiq again for his wonderful work. So we're going to now proceed with our ceremony. So we're going to present a plaque and a certificate and also prize money to our winner of this year's Best Research Paper Award. So all of our junior researchers, including PhD students, assistants, and also postdoc, please, you can enter this event, and we're gonna maybe from the next year we're gonna do it in March instead of the October, so we can cover the full 2 years of the work. Okay, so we're gonna make a judgment, and hopefully we'll get more entrants. So make this award more prestigious. All right. So, okay. Now, can I ask Zixun come over? Yeah. Also, together we can. Let me present this the certificate later. Okay. Yeah. Also. Okay, that's congratulations. Okay, now we're gonna So please stay for the our colloquium today. Maybe we can invite our speakers come in. Wen Hao, still outside.